April 12, 1937, RAF Cranwell, Lincolnshire, England. The spinning metal disc screamed at 13,000 revolutions per minute inside a makeshift test rig cobbled together from scrap metal, bicycle parts, and borrowed laboratory equipment. Flight Lieutenant Frank Whittle stood in the corner of a converted garage, his ears protected by cotton wool, watching his colleagues exchange glances that said everything without words. Another crackpot inventor chasing an impossible dream. The prototype turbojet engine, officially designated the Whittle unit, produced exactly 480 pounds of thrust, not enough to lift a child's bicycle. The assembled RAF officers, summoned to witness what Whittle had promised would revolutionize aviation, struggled to hide their disappointment. Air Vice Marshal Hugh Dowding, present at the insistence of the Air Ministry, checked his watch after 15 minutes and departed without comment. His assessment, recorded in official notes discovered decades later, was brutally concise. Interesting theoretical exercise, no practical military application foreseeable. What none of them knew, what none of them could have imagined, was that the screaming contraption in that garage would render obsolete every military aircraft in existence within a decade. The spinning disc they dismissed would evolve into engines producing 50,000 pounds of thrust. The impossible dream they mocked would carry men faster than sound and higher than mountains. Within 8 years, jet fighters would dominate the skies over Europe, changing aerial warfare forever. But in April 1937, Frank Whittle was just another junior officer with theories nobody wanted to hear, building an engine nobody believed would work, solving problems nobody thought were worth solving. The mathematics of revolution were being written in a garage in Lincolnshire, dismissed by experts who couldn't see past their own assumptions about what was possible. The journey to that garage had begun 9 years earlier, in the mind of a 21-year-old RAF cadet who couldn't stop thinking about a single question: why do aircraft engines get weaker the higher you fly? January 1928, RAF College, Cranwell. Frank Whittle, son of a mechanical engineer from Coventry, submitted his final thesis for officer training. The title was modest: Future Developments in Aircraft Design. The content was revolutionary. While his classmates wrote about incremental improvements to existing piston engines, Whittle proposed abandoning them entirely. The problem, as Whittle saw it, was fundamental. Piston engines required air to burn fuel. The higher an aircraft climbed, the thinner the air became. Every additional 1,000 feet of altitude robbed the engine of power. Superchargers helped, forcing more air into the cylinders, but they added weight, complexity, and their own diminishing returns at extreme altitude. Whittle's solution was elegantly simple in theory. Instead of using pistons to compress air, why not use the engine's own exhaust to spin a turbine, which would compress incoming air continuously? The compressed air would mix with fuel in a combustion chamber, creating expanding gases that would both spin the turbine and provide thrust directly from the exhaust. A continuous cycle of compression, combustion, and expansion. No pistons, no cylinders, no mechanical limit to how fast the engine could spin or how much thrust it could produce. His instructors gave him a passing grade and forgot about it. The Air Ministry, when they eventually reviewed it, filed the thesis under Future Developments Not Required. In 1928, the RAF was flying biplanes with open cockpits. Jets were science fiction. But Whittle couldn't let it go. While serving as a flight instructor at RAF Wittering, he spent his spare time working through the mathematics. The theoretical efficiency was stunning. A jet engine could operate at altitudes where piston engines suffocated. It could achieve speeds that would tear propeller blades apart from centrifugal force. The thrust-to-weight ratio exceeded anything possible with conventional engines. In January 1930, Whittle filed British Patent 347206 for a method of and means for generating propulsive force. The Patent Office accepted it. The Air Ministry declined to fund development. The British aircraft industry, drowning in Depression-era financial troubles, showed no interest. The patent, which would have given Britain a monopoly on jet propulsion, was allowed to lapse in 1935 for non-payment of the $5 renewal fee. The rejection stung, but it also freed Whittle from military restrictions. If the government wouldn't build his engine, he would build it himself. In March 1936, with £2,000 raised from private investors and support from two former RAF colleagues, officers Rolfe Dudley Williams and James Tinling, Whittle established Power Jets Ltd. The company operated from a garage in Rugby, leased from British Thomson Houston. The staff consisted of Whittle, two mechanics, and whatever university students they could convince to help. The first design, designated the WU for Whittle unit, existed only on paper for 6 months. Every component had to be designed from scratch. No textbooks existed on turbine blade metallurgy for continuous high-temperature operation. No manufacturer produced bearings capable of operating at the required speeds. No fuel pumps could handle the pressure. They were inventing not just an engine, but an entirely new engineering discipline. The compressor presented the first major challenge. Whittle's design used a double-sided centrifugal compressor, a rotating disc with vanes that would fling air outward at high speed, compressing it through centrifugal force. The mathematics were straightforward. The engineering was anything but. At 13,000 RPM, the outer edge of the compressor disc traveled at over 1,000 feet per second. Any imbalance, any flaw in the metal, any miscalculation in the blade angles would cause catastrophic disintegration. William Tinling, one of the company's two mechanics, machined the first compressor disc from solid steel using equipment borrowed from a local machine shop. The tolerances were measured in thousandths of an inch. A single burr on a blade edge could create vibrations that would shake the entire assembly apart. The disc took 3 weeks to complete. When they finally mounted it on the test rig, it lasted exactly 47 seconds before friction bearings seized from thermal expansion. The disc slowed from 13,000 RPM to 0 in less than 2 seconds, the deceleration so violent it cracked the housing. They redesigned the bearings. The second test lasted 4 minutes before lubricating oil, unable to withstand the heat, caught fire. They changed the oil system. The third test ran for 20 minutes before the combustion chamber, cobbled together from welded steel sheets, warped from thermal stress and began leaking flame. Each failure taught them something nobody had known before. They discovered that ordinary steel became brittle at the temperatures inside a jet engine. They learned that combustion didn't happen uniformly at high pressure, creating hot spots that could melt metal. They found that starting a jet engine required a precisely choreographed sequence of fuel flow, air pressure, and ignition timing. Too much fuel, and you got a fire. Too little, and nothing happened. The window between success and disaster was measured in fractions of a second. By the time of the April 1937 demonstration, they had burned through most of their funding and all of their investors' patience. The engine that ran for 15 minutes that day represented 18 months of work, 100 failures, and the development of entirely new engineering techniques. The 480 pounds of thrust was pathetic by later standards, but it proved the concept worked. Air went in one end, got compressed, mixed with fuel, burned, spun a turbine, and produced thrust. The cycle was self-sustaining once started. They had built the world's first practical turbojet engine. The RAF officers who witnessed it saw a noisy, temperamental machine that produced less thrust than the propellers on a training aircraft. They missed the point entirely. What Whittle had demonstrated wasn't a finished product, it was proof that the entire future of aviation had just changed. The Air Ministry's official response, delivered in May 1937, acknowledged Whittle's interesting achievement, but concluded that the practical difficulties of metallurgy, fuel consumption, and operational complexity make military application unlikely in the foreseeable future. They were particularly concerned about fuel consumption. The WU burned fuel at a rate that would empty a fighter aircraft's tanks in less than 30 minutes. For sustained flight, they calculated a jet fighter would need to carry more fuel than bombs, making it useless as a weapons platform. What the Air Ministry failed to understand was that they were calculating based on existing flight parameters. Yes, a jet engine burned more fuel per minute than a piston engine, but it could fly higher and faster, reducing flight time. A mission that took a piston-engined fighter 45 minutes might take a jet 20. The fuel consumption per mission could actually be lower, even with the higher burn rate. Whittle understood this. His investors did not. By autumn 1937, Powerjets Limited was effectively bankrupt. Whittle, still a serving RAF officer, was recalled to active duty. The company went dormant. The world's first jet engine sat in a garage in Rugby, gathering dust, its revolutionary potential unrealized because nobody could see past the immediate limitations to the ultimate possibilities. Then Germany invaded Poland. September 3, 1939, Britain declared war on Germany. Within weeks, the Air Ministry began frantically reassessing every aircraft project they had previously dismissed. Someone remembered the strange engine in Rugby. In November, Whittle received orders to revive Powerjets and prepare a flight-worthy engine with utmost priority. The government provided £100,000, a proper facility at the British Thomson-Houston Works in Rugby, and access to the nation's best engineers. The conditions were clear: produce a flyable jet engine in 18 months or the project would be cancelled. The timeline was impossibly aggressive. They were being asked to perfect in a year and a half what conventional engine development would require a decade to achieve. Whittle's team expanded to 50 engineers and mechanics. They worked 16-hour days, 7 days a week. The WU design was completely revised, designated the W1 for military service. The compressor was enlarged, the combustion chamber redesigned, the turbine blades cast from new nickel alloys, developed specifically for high-temperature operation. The metallurgy alone was revolutionary. Turbine blades experienced temperatures exceeding 1,500 degrees Fahrenheit while spinning at 16,000 RPM, subjecting them to centrifugal forces of over 10,000 times gravity. The blades had to be strong enough to withstand these forces, heat-resistant enough not to deform, and precisely shaped to maintain aerodynamic efficiency. Standard aircraft aluminum would melt instantly. Steel would warp. They needed something that didn't exist yet. Dr. Hayne Constant, a metallurgist assigned to the project from the Royal Aircraft Establishment, developed a nickel-chromium alloy with trace elements of titanium and aluminum. The formula was classified secret, the designation mnemonic 80. Individual turbine blades were investment cast, a process borrowed from jewelry making, where molten metal is poured into ceramic molds created from wax patterns. Each blade required its own mold. The rejection rate exceeded 60%. A single microscopic flaw, a tiny air bubble, an uneven cooling pattern, would cause failure at operating speeds. The combustion chamber presented different challenges. Earlier designs had used a simple tube where fuel and compressed air mixed and burned. At the increased pressures and fuel flows of the W1, this created a blowtorch effect that melted the chamber walls within minutes. They needed a design that would sustain continuous combustion without destroying itself. Whittle's solution was brilliantly counterintuitive. Instead of one large combustion zone, he created 10 separate flame tubes arranged in a ring around the engine core. Compressed air from the centrifugal compressor was divided between these chambers, creating smaller, more controllable combustion zones. Each chamber was lined with perforated steel, allowing a thin film of cool air to flow along the walls, insulating them from the flame. The hottest gases stayed in the center of each tube, never touching the metal directly. The fuel delivery system was equally critical. Unlike a piston engine with its precisely timed injectors, a jet engine needed continuous fuel flow that would automatically adjust to changes in throttle, altitude, and temperature. Too much fuel, and the engine would overheat or flame out from excessive back pressure. Too little, and it would lose power or fail to relight after throttle changes. They developed a hydromechanical fuel control unit, a masterpiece of precision engineering that used a combination of springs, diaphragms, and metering valves to sense engine speed, compressor pressure, and burner temperature, adjusting fuel flow automatically to maintain optimal combustion. The unit weighed 28 pounds and contained over 200 individual parts, each machined to tolerances of 1/10,000th of an inch. It was, in effect, a mechanical computer designed for a single purpose: keeping a jet engine alive. By March 1941, the W-1 was ready for ground testing. The engine weighed 623 pounds and produced 860 pounds of thrust at 16,500 RPM. That was enough, barely, to propel a small aircraft at speeds competitive with piston fighters. But the real advantage was altitude. While conventional fighters struggled above 30,000 feet, their engines gasping in thin air, the W-1's performance actually improved with altitude. The colder air increased density. The reduced back pressure from thinner atmosphere improved exhaust flow. And the lower ambient temperature helped cool the engine internally. The test cell at British Thomson Houston was a reinforced concrete bunker with 3-foot-thick walls, built to contain the engine if it exploded. Everyone expected it would. The first full-power test was scheduled for April 12, 1941, exactly 4 years after the original garage demonstration. This time, representatives from the Air Ministry, the Ministry of Aircraft Production, and Gloster Aircraft Company attended. Nobody was laughing anymore. At 2:17 p.m., Whittle gave the signal to start. The electric starter motor spun the compressor to 2,000 RPM. Fuel flow began. Ignition. The engine lit with a deep, thunderous roar completely unlike any aircraft engine anyone had heard before. No staccato piston beats, no propeller blade whine, just a continuous building howl as the RPMs climbed. 5,000, 10,000, 15,000. The roar became a scream. The test cell shook. Instruments showed 860 pounds of thrust. The engine ran for 30 minutes at full power without failure. Wing Commander Harold Tubby Grant of the Air Ministry wrote in his official report, "Witnessed sustained operation of Whittle turbojet at rated output. Performance exceeds projections. Recommend immediate integration with airframe for flight testing. This engine represents the future of military aviation." 2 months later, the W-1 was installed in the Gloster E-2839, a small experimental aircraft built specifically to test jet propulsion. The aircraft was tiny, with a 29-foot wingspan and empty weight of just 2,800 pounds. The fuselage was essentially a tube wrapped around the W-1 engine, with stubby wings and a tail. It looked, according to test pilot Flight Lieutenant Jerry Sayer, like a pregnant tadpole. May 15, 1941, 7:40 p.m., RAF Cranwell, the same airfield where Whittle had demonstrated his first test rig 4 years earlier. Flight Lieutenant Sayer taxied the E-2839 to the end of runway 26 as ground crew and military observers watched from a distance behind blast shields, expecting disaster. No ejection seat existed. If the engine failed, Sayer's survival would depend on his ability to glide the aircraft down from whatever altitude he reached. Sayer advanced the throttle. The jet engine spooled up with that characteristic howl. The small aircraft accelerated smoothly down the runway, none of the propeller torque that wanted to twist conventional fighters off the center line. At 80 miles per hour, Sayer eased back on the stick. The E-2839 lifted off after a ground roll of just 600 feet. The flight lasted 17 minutes. Sayer climbed to 8,000 feet, performed gentle turns, and tested the engine response at different power settings. The controls were light and responsive, The aircraft handled smoothly. Most significantly, the engine ran flawlessly throughout. When Sayre landed and climbed out of the cockpit, he was grinning. "It flies beautifully. The engine is as smooth as silk. This is going to change everything." The E-2839 flight demonstrated conclusively that jet propulsion worked in the air as well as on the ground. The aircraft reached 370 miles per hour in level flight, competitive with the best piston fighters of 1941. More importantly, it maintained full power at altitudes where conventional fighters struggled. During a test flight in March 1942, test pilot Flight Lieutenant John Grierson took the E-2839 to 42,000 feet, higher than any RAF aircraft had ever flown operationally. But while the E-2839 proved the concept, it was never intended as a combat aircraft. It was a flying test bed, a proof of principle. The real question was whether jet propulsion could be translated into an operational fighter that would give the RAF a decisive advantage. Gloster Aircraft received a contract in February 1941, even before the E-2839 flew, to develop the Gloster F940, Britain's first jet fighter. The specifications were ambitious: 400 miles per hour top speed, service ceiling of 40,000 feet, endurance of 1 hour, armed with 4 20mm cannons. The engine would be an enlarged version of Whittle's design, designated the WWII, producing 1,600 pounds of thrust. The problem was time. German bomber raids were intensifying. The Battle of Britain had been won, barely, by Spitfires and Hurricanes. But intelligence reports indicated Germany was developing their own jet engines. The race was on to get a jet fighter operational before the Germans did. Engineer George Carter, chief designer at Gloster, took an unconventional approach. Instead of designing an entirely new airframe optimized for jet propulsion, he adapted the wing and tail surfaces from Gloster's conventional fighter designs, mounting them on a new fuselage built around twin W2 engines. Twin engines provided redundancy and additional thrust, critical for an aircraft carrying the weight of cannons and ammunition. The decision to use two engines was controversial. It added weight and complexity. But it solved a critical problem. Single-engine thrust was barely adequate for a fully loaded combat aircraft. With two engines, the fighter would have power to spare for high-speed climbs and sustained combat maneuvering. If one engine failed, the aircraft could return to base on the other. The Gloster Meteor, as the F9x40 was named, first flew on March 5, 1943 at RAF Cranwell. Test pilot Michael Daunt took off on the power of two W2 engines and reached 380 miles per hour during the initial flight. Subsequent test flights revealed some handling quirks. The twin engines mounted in wing nacelles created unusual aerodynamic effects, but overall performance exceeded expectations. By July 1944, as Allied forces consolidated their hold on Normandy, the first operational Meteor F-1s entered service with no 1616 Squadron RAF. They were deployed specifically to counter Germany's V-1 flying bombs, the Doodlebugs, terrorizing London. The V-1s flew at 400 miles per hour, too fast for most piston fighters to catch reliably. The Meteors could reach 410 miles per hour in level flight and sustain that speed long enough to intercept and destroy the flying bombs. Flying Officer T.D. Dixie Dean scored the first Meteor victory on August 4, 1944. Unable to fire his cannons, which had jammed, Dean positioned his Meteor's wingtip under the V-1's wing and tipped it over, disrupting its gyroscopic guidance and sending it into a terminal dive. The tactic was dangerous. The Meteor had to match speeds within feet of the V-1's wing, but it worked. By war end, no 1616 Squadron had destroyed 14 V-1s with no aircraft losses. More significantly, they had proven that jet fighters were operationally viable. Maintenance crews learned to service the temperamental engines, pilots adapted their tactics to exploit the jet's straight-line speed advantage while avoiding turning fights where piston fighters still held the edge. But while Britain was methodically developing jet propulsion through careful engineering and testing, Germany was pursuing the same technology with desperate urgency, and they were ahead. August 27, 1939, 1 week before Germany invaded Poland. The Heinkel HE-178 lifted off from Rostock-Marienhütte airfield in northeastern Germany, powered by a single HE-S-3B turbojet engine designed by Dr. Hans von Ohain. The flight lasted 6 minutes and reached speeds of 360 miles per hour. Germany had achieved powered jet flight 20 months before Britain's E-2839 would take to the air. The parallel development of jet engines in Britain and Germany stands as one of history's most remarkable cases of simultaneous invention. Frank Whittle and Hans von Ohain worked independently, neither knowing of the other's existence until after the war, yet arrived at nearly identical solutions to the same problems. Von Ohain, a physics doctoral student at the University of Göttingen, Germany, filed his first jet engine patent in 1934, 4 years before Whittle. But while Whittle struggled for funding, von Ohain found immediate support from Ernst Heinkel, the aircraft manufacturer, who saw military potential. By 1937, von Ohain had a working engine. By 1939, he had an aircraft in the air. The HE-178 was never intended as a combat aircraft. It was a proof-of-concept demonstrator, smaller and lighter than the later E-2839. But it showed German engineering leadership that jet propulsion was practical. The Luftwaffe, initially skeptical, began funding jet fighter development in 1939. The result was the Messerschmitt Me-262, the world's first operational jet fighter. First flew in July 1942, it entered combat in July 1944, 3 months before the Meteor. The Me-262 was by any measure the most advanced fighter aircraft of World War II. Twin Junkers Jumo 004 turbojet engines, each producing 1,980 pounds of thrust, gave it a top speed of 540 miles per hour, nearly 100 miles per hour faster than any Allied fighter. 4 30mm cannons provided devastating firepower. Its swept-wing design, though aerodynamically less efficient than straight wings at low speeds, allowed it to maintain stability at speeds where conventional fighters would buffet and shake apart. German test pilots who flew the Me-262 described it in terms that mixed awe with terror. Lieutenant Fritz Müller, an experienced fighter pilot with 73 victories in Bf-109s, flew the Me-262 for the first time in October 1944. The acceleration was unlike anything I had experienced. You advanced the throttle, and the aircraft leaped forward, pressed you back into the seat. Within seconds, you were traveling faster than your mind could process. Allied fighters appeared to be standing still. You overtook them before they knew you were there. The firepower was equally revolutionary. Each 30mm Mk-108 cannon fired 650 rounds per minute, with each shell containing 85 grams of high explosive. A single hit could blow the wing off a bomber. 3 or 4 hits guaranteed a kill. In the hands of an experienced pilot, the Me-262 was a bomber destroyer without equal. Allied bomber crews called it the blow job for the distinctive sound its engines made, a sharp whistle that signaled incoming death. When Me-262s attacked, the standing orders were simple. The bomber formation broke up and individual aircraft tried to evade. Staying in formation meant certain destruction. The statistics were terrifying. During the period of Me-262 operations from July 1944 to April 1945, jet fighters accounted for approximately 500 Allied aircraft destroyed against the loss of about 100 Me-262s. That was a 5-to-1 kill ratio, better than any German fighter had achieved since 1942. If Germany had deployed the Me-262 in significant numbers earlier in the war, the strategic bombing campaign might have failed. But they didn't, and the reasons why reveal both the genius and the fatal flaws of German wartime engineering. The Me-262's development was plagued by delays, not from engineering failures, but from political interference. Adolf Hitler, shown the prototype in November 1943, became obsessed with the idea of using it as a high-speed bomber to retaliate for Allied raids on German cities. He ordered the Me-262 redesigned to carry bombs, despite the aircraft being optimized as an interceptor. The fighter-bomber variant, designated the Me-262A2A Sturmvogel, Stormbird, could carry two 550-pound bombs. But the additional weight degraded performance, reduced range, and required structural modifications that delayed production by months. Worse, the bombing mission required completely different pilot training and tactics. Fighter pilots trained in air-to-air combat were suddenly expected to conduct ground attack missions in an aircraft too valuable to risk at low altitude. Oberst Adolf Galland, general of the fighter arm, fought Hitler's decision with increasing desperation. In reports that nearly cost him his career, Galland argued that the Me-262's proper role was bomber interception. He calculated that 300 Me-262s operating as pure fighters could effectively end the Allied daylight bombing campaign within months. The speed advantage would make them nearly immune to fighter escort, while their heavy cannons would annihilate bomber formations. Hitler refused. The Me-262 would be his blitz bomber, his revenge weapon. It wasn't until November 1944, with Germany clearly losing the war, that Hitler reluctantly authorized fighter variants. By then, it was too late. Allied advances had captured key manufacturing facilities. Fuel shortages limited operations. Trained pilots were dead or captured. But even with these handicaps, the Me-262 demonstrated what might have been. In March 1945, Jagdverband 44, Fighter Unit 44, commanded by Galland himself and staffed by some of Germany's most experienced aces, became operational at Munich-Riem Airfield. Flying pure fighter versions of the Me-262, they achieved kill ratios exceeding 10-to-1 against Allied aircraft. Lieutenant Colonel Elwin Rigetti, commanding officer of the 55th Fighter Group, was shot down and killed by a Me-262 on April 17, 1945, 3 weeks before Germany surrendered. His final transmission was recorded. "Bandit, 6 o'clock, closing fast. Jesus, he's..." The Me-262 that killed him fired a single 1-second burst that blew Rigetti's P-51 apart at 400 yards range. The German pilot, never identified, disappeared into clouds before Rigetti's wingmen could react. The technological superiority was undeniable, but technology alone doesn't win wars. Germany produced approximately 1,400 Me-262s. Only about 200 saw combat. Chronic fuel shortages kept most grounded. Lack of trained pilots meant many were never flown. Allied bombing destroyed engines before they could be installed. The few that reached operational units faced overwhelming numbers of Allied fighters that would swarm them during takeoff and landing, when jets were most vulnerable. The most revealing statistic? Germany had the world's most advanced fighter aircraft flying combat missions in mid-1944. They still lost the war less than a year later. The Me-262 was a masterpiece of engineering rendered irrelevant by strategic failure. While Germany deployed jets in combat and Britain methodically developed the Meteor, America had been watching with interest. The U.S. Army Air Forces were briefed on Whittle's engine in September 1941, just months after the E-28/39's first flight. In October, A Whittle W1X engine was shipped to America under utmost secrecy, escorted by British engineers who would assist with American development. General Electric, with extensive experience in turbo superchargers, received the contract to develop an American version. The result was the General Electric IA, producing 1,250 pounds of thrust, first run in April 1942. Bell Aircraft was contracted to design an airframe around the engine, resulting in the Bell XP-59A Aerocomet. The Aerocomet first flew on October 1, 1942, at Muroc Dry Lake in California, later to become Edwards Air Force Base. The flight was witnessed by few people and photographed by none. The entire program was classified top secret. To maintain secrecy, a dummy propeller was attached to the aircraft when it was moved, making it appear to be a conventional fighter to casual observers. The XP-59A performed reasonably well in testing, reaching 404 miles per hour and demonstrating the smooth handling characteristics of jet propulsion. 66 aircraft were eventually produced. But the Aerocomet had a fatal flaw. It wasn't significantly better than existing piston fighters. The P-51 Mustang could match its speed, exceeded its range, and was already in mass production. The Aerocomet never saw combat, serving instead as a trainer to familiarize American pilots with jet operations. But American engineers learned valuable lessons from the Aerocomet program. They learned about high-temperature metallurgy. They learned about fuel control systems. They learned about the operational challenges of maintaining jet engines. When the time came to develop America's first operational jet fighter, that knowledge proved invaluable. The Lockheed P-80 Shooting Star emerged from a requirement issued in June 1943 for a jet fighter superior to the Me-262. Lockheed's legendary Skunk Works, led by Clarence Kelly Johnson, promised to deliver a prototype in 180 days. They completed it in 143 days, one of the most remarkable achievements in aviation history. The XP-80 first flew on January 8, 1944, powered by a British de Havilland Goblin turbojet. It reached 502 miles per hour during initial testing, faster than any American aircraft flying at the time. The production P-80A, powered by an American-designed Allison J-33 engine, would exceed 580 miles per hour, competitive with the Me-262. But the P-80 arrived too late for combat in World War II. The first production aircraft weren't delivered until December 1945, 7 months after Germany surrendered. 2 P-80s did reach Italy in April 1945 for operational testing, but the war in Europe ended before they could see action. The delay was deliberate. American commanders watching the Me-262's troubled operational history concluded that introducing a new aircraft type in the final months of war created more problems than it solved. Maintenance infrastructure would need to be established, pilots would need training, tactics would need to be developed, all while fighting a war. Better to wait, perfect the design, and introduce it properly in peacetime. That decision highlighted a fundamental difference in how America and Germany approach technology. Germany, desperate for a war-winning weapon, rushed jets into service with inadequate testing, insufficient pilot training, and no proper maintenance infrastructure. America, confident of victory, took time to do it right. By war's end, 3 nations had operational jet fighters. Britain had logged the most jet flight hours and developed the most reliable engines. Germany had the most combat experience and the fastest aircraft. America had the industrial capacity to mass-produce jets in quantities that would make them ubiquitous in post-war aviation. The true revolution, though, wasn't just the jet fighters themselves, it was what they represented. The complete transformation of aerial warfare. Everything that pilots and engineers had learned about aircraft design over 4 decades of powered flight was suddenly obsolete. Propeller fighters were limited by propeller efficiency, which degraded rapidly above 400 miles per hour as blade tips approached supersonic speeds. Jet fighters had no propellers. They could fly faster, limited only by the aircraft's structural strength and the onset of transonic effects. Piston engines lost power with altitude, their performance degrading above 30,000 feet. Jet engines improved with altitude, operating more efficiently in cold, thin air. The operational ceiling of jet fighters would eventually exceed 50,000 feet, twice the altitude of piston fighters. Piston engines required complex reduction gearing to convert high RPM engine output to usable propeller speeds. Jets produced thrust directly, eliminating an entire mechanical subsystem and its associated weight. But jets brought new challenges. Fuel consumption was high, limiting range. Engine reliability was poor, with early jets requiring complete engine overhauls after just 25 hours of operation, compared to hundreds of hours for piston engines. High-speed flight introduced compressibility effects that made aircraft difficult to control near the speed of sound. Most significantly, jets required entirely new tactics. Everything fighter pilots knew about combat was based on aircraft that could turn and climb. Jets were fast, but initially less maneuverable. Dogfighting tactics developed over decades became obsolete overnight. New tactics based on speed and energy management had to be invented. The German pilots who flew the Me-262 operationally were pioneers in this new form of warfare. They developed the hit-and-run tactic: dive from high altitude at maximum speed, fire a quick burst at bombers, then use excess speed to climb back to altitude before Allied escorts could react. Turning to fight Allied fighters was suicide. The Me-262 could outrun anything, but it couldn't outturn a P-51. Major Walter Novotny, one of Germany's highest-scoring aces, with 258 victories, was killed flying an Me-262 on November 8, 1944. His mistake was trying to dogfight. After destroying a B-24 bomber, Novotny turned to engage pursuing P-51s instead of using his speed advantage to escape. The Mustangs, flown by experienced pilots who had learned how to exploit the Me-262's weaknesses, forced him into a turning fight. At low altitude, low speed, the jet became a target. Multiple P-51s hit Novotny's aircraft. It crashed in flames. The pilot who had mastered piston engine combat died because he tried to apply old tactics to a new aircraft. The lesson was clear. Jet fighters required not just new engineering, but new thinking. Pilots trained in traditional combat maneuvers needed to unlearn everything and start fresh. The learning curve was deadly. By May 1945, as Germany surrendered, the jet age had definitively arrived. Over 1,400 Me-262s had been produced. Britain had over 200 Meteors in service. America had dozens of P-80s undergoing testing. The Soviet Union, always secretive, had developed their own jet fighters, based partly on captured German engines and partly on British engines provided under wartime cooperation agreements. The post-war world would belong to jets. Propeller fighters, no matter how advanced, were obsolete. The North American P-51 Mustang, considered by many to be the finest piston fighter ever built, was retired from frontline service by 1950. The jet fighters that replaced it could fly twice as fast and twice as high. But the transformation went beyond just fighter aircraft. The jet engine principle, continuous compression and combustion, could scale to any size. Engines producing 100,000 pounds of thrust would eventually power commercial airliners, carrying hundreds of passengers across oceans. Turbofan engines, descendants of Whittle's original design, would make air travel affordable and routine. The strategic implications were equally profound. Jet aircraft could cross continents in hours. Jet bombers could strike targets thousands of miles away. Jet fighters could intercept bombers at altitudes where human pilots needed pressure suits to survive. The entire concept of air defense had to be rethought. In the immediate post-war period, a bitter fight erupted over credit for inventing the jet engine. Britain claimed Whittle as the inventor. Germany claimed von Ohain. America, having produced neither, but having the strongest post-war aviation industry, largely ignored the debate and focused on development. The reality was that both Whittle and von Ohain independently invented practical turbojet engines. Whittle filed patents first. Von Ohain flew first. Both faced similar technical challenges and arrived at similar solutions. Both were brilliant engineers working with inadequate resources to create something revolutionary. What's remarkable is how close they came to never succeeding at all. Whittle nearly abandoned his engine in 1937 when funding ran out. Von Ohain's engine nearly destroyed itself during early tests, coming within seconds of catastrophic failure multiple times. The margin between success and failure, between revolution and obscurity, was measured in lucky breaks and stubborn persistence. In 1978, Frank Whittle and Hans von Ohain met for the first time at the United States Air Force Museum in Dayton, Ohio. Both were elderly men by then, their contributions finally receiving proper recognition. They spent hours comparing notes, laughing about similar problems, amazed at how parallel their work had been despite complete independence. Von Ohain, through an interpreter, told Whittle, "We both created the same thing, neither knowing of the other. This proves that the idea's time had come. If you had failed, I would have succeeded. If I had failed, you would have succeeded. The jet engine was inevitable."
Whittle responded, "Perhaps. But knowing how close I came to failing completely, how many times I nearly gave up, I'm not so certain. We were both impossibly stubborn men who refused to accept what experts told us was impossible. The world needs more stubborn fools." The statistics of their combined achievement are staggering. Whittle's development: first patent filed 1930, first engine run 1937, first flight 1941, first operational fighter 1944. Total development time 14 years. Total funding through 1944, approximately £500,000. Von Ohain's development: first patent filed 1934, first engine run 1937, first flight 1939, first operational fighter 1944. Total development time 10 years. Total German funding approximately 8 million Reichsmarks. Aircraft produced during World War II: Britain, approximately 200 Meteor fighters. Germany, approximately 1,400 Me-262 fighters. America, 66 P-59 trainers, minimal P-80 production before war's end. Combat victories: Me-262, approximately 500 Allied aircraft destroyed. Meteor, 14 V-1 flying bombs destroyed. P-59, 0, never saw combat. P-80, 0, arrived too late. The post-war statistics are even more revealing. By 1950, every major air force had transitioned to jets. By 1960, propeller-driven fighters were museum pieces. By 1970, jet engines powered 95% of commercial aviation. By 2000, the total number of turbojet and turbofan engines produced exceeded 500,000 units. The man who started it all, Frank Whittle, received a knighthood in 1948 and £100,000 from the British government for his invention, a pittance considering his contribution. He emigrated to America in 1976 and died in 1996 at age 89. Hans von Ohain worked for the U.S. Air Force after the war, contributing to American jet engine development. He died in 1998 at age 86. Neither man profited significantly from their invention. The patents were declared essential to national security and effectively nationalized. The commercial benefits went to large corporations that could manufacture engines at scale. Whittle and von Ohain received recognition but not wealth. Yet their impact is incalculable. Every jet airliner in service today uses engines descended from their designs. Every military jet fighter traces its lineage to their work. The entire global economy, dependent on rapid air transportation, exists because two engineers refused to accept that their impossible dream couldn't become reality. The garage in Rugby where Whittle built his first engine no longer exists, demolished decades ago. A plaque marks the location. The Heinkel facility where von Ohain worked was destroyed during the war, bombed by the very forces whose victory jets would eventually ensure. The physical locations are gone, but the revolution they launched continues. In April 2037, 100 years after Whittle's first engine ran in that Rugby garage, commercial hypersonic aircraft may routinely carry passengers from London to New York in under 2 hours. The engines powering those aircraft, whether scramjets or some yet unimagined propulsion system, will be direct descendants of the spinning disk that RAF officers mocked in 1937. The story of the jet engine is ultimately a story about vision overcoming skepticism, about persistence defeating adversity, about the power of a single idea to change everything. Frank Whittle saw beyond the limitations of piston engines to a future where aircraft could fly faster and higher than anyone thought possible. Hans von Ohain independently reached the same vision. Together, unknowingly, they rendered obsolete every aircraft in existence and launched a revolution that continues to this day. The RAF officers who dismissed Whittle's engine in 1937 weren't stupid. They were rational men making reasonable judgments based on available evidence. The engine produced insufficient thrust. It consumed too much fuel. It was temperamental and unreliable. By every conventional metric, it was impractical. What they couldn't see was that the limitations were temporary, technical problems waiting to be solved, while the potential was permanent, a fundamental breakthrough in propulsion. They evaluated the prototype without imagining what it could become. That failure of imagination was forgivable in 1937. It would be inexcusable today. The lesson of Whittle's jet engine, like the lessons of countless other revolutionary technologies, is that the prototype is not the product. The early version, crude and limited, may bear little resemblance to the mature version that changes the world. The spinning disk in that Rugby garage looked like a curiosity. It was actually a glimpse of the future. The screaming monster that terrified everyone who heard it would eventually become the smooth, reliable turbofan engine that most people never think about as it carries them safely across continents and oceans. Frank Whittle died believing he had failed to receive proper credit for his invention. The patents had lapsed. The British government had appropriated his work. American and German engineers had improved on his designs. His name was known to aviation historians, but forgotten by the public. Yet every time a jet airliner takes off, carrying hundreds of passengers to destinations that would have taken weeks to reach in 1937, Frank Whittle's vision becomes reality again. Every time a military jet fighter accelerates to supersonic speeds at altitudes where the sky turns black and the curvature of Earth becomes visible, Whittle's dream lives on.
The mad engineer who built a jet engine in his garage didn't just change World War II, he changed the world. The laughter of skeptics who dismissed him in 1937 was drowned out by the thunder of millions of jet engines that followed. That thunder, the sound of continuous combustion spinning turbines at impossible speeds, is the sound of the future arriving. And it all began with a question nobody thought was worth asking. Why do aircraft engines get weaker the higher you fly? The answer to that question, developed by a stubborn RAF officer in a Rugby garage, revolutionized human flight, shortened the world, and proved that the impossible is only impossible until someone builds it. The jet age began not with a victory, but with ridicule. It succeeded not through official support, but through stubborn persistence. And it continues not because of the men who invented it, long since dead, but because their vision, once mocked, proved unstoppable. They laughed at the spinning metal contraption. Now jet engines carry 8 billion people's dreams across skies their inventors barely imagined. Frank Whittle and Hans von Ohain didn't just build engines. They also developed the concept of jet propulsion. They built the future. And the future screamed. The transformation wasn't immediate, it wasn't clean, and it certainly wasn't cheap. Between 1945 and 1950, the major air powers spent billions developing jet technology that mostly didn't work. Engines seized, turbine blades disintegrated, fuel systems failed. Pilots died in crashes caused by flameouts, compressor stalls, and a dozen other failures that didn't have names yet because nobody had experienced them before. The United States Air Force, established as an independent service in 1947, lost 776 aircraft to accidents in 1952 alone. Many were jets. The casualty rate among jet pilots exceeded that of bomber crews over Germany. Young men who had survived World War II died testing aircraft that represented the future but killed with present regularity. Lieutenant Colonel Frank Everest, chief test pilot at Edwards Air Force Base, summarized the era in a 1953 interview. "We're learning how to fly at speeds and altitudes where humans don't belong. Every flight teaches us something. Sometimes the lesson kills the pilot. We write it down and the next pilot learns from it. That's progress, written in blood and wreckage." The Korean War, erupting in June 1950, provided the crucible where jet combat doctrine was forged. When North Korean forces crossed the 38th parallel, the United States Air Force deployed F-80 Shooting Stars, Lockheed's improved version of the P-80. The Soviets, supporting North Korea, deployed MiG-15s, their first swept-wing jet fighter. The MiG-15 shocked Western air forces. Powered by a reverse-engineered copy of the British Rolls-Royce Nene engine, ironically sold to the Soviets by Britain in 1946, it could reach 668 miles per hour and climb to 50,000 feet. It was faster, climbed better, and flew higher than any American fighter in theater. November 1, 1950. Lieutenant Russell Brown, flying an F-80C, encountered a MiG-15 near the Yalu River. The engagement lasted less than 2 minutes. Brown, using tactics learned from P-51 pilots who had fought Me-2062s, refused to dogfight. Instead, he used diving attacks, exploiting the F-80's superior low-altitude acceleration. His .50 caliber guns hit the MiG's fuselage. The Soviet fighter, piloted by Senior Lieutenant Karatonov, went down trailing smoke. It was the first jet versus jet victory in history. But Brown's victory was an anomaly. The F-80, based on 1943 technology, was outclassed. American pilots needed a fighter that could match the MiG-15. They got the North American F-86 Sabre, a swept-wing design that had been in development since 1947. The F-86 arrived in Korea in December 1950. It was, in every respect, a product of lessons learned from German jet development. The wings were swept at 35 degrees, copying the MAD 2062's approach to delaying compressibility effects. The engine, a General Electric J-47, produced
5,200 pounds of thrust, more than 3 times Whittle's original W1. The armament consisted of 6.50 caliber machine guns, maintaining the American philosophy of volume firepower over individual shell power. What followed was the world's first sustained jet versus jet combat. Over an area of North Korean airspace near the Yalu River, nicknamed MiG Alley, American Sabres and Soviet MiGs fought daily battles that established the template for jet combat. The tactics were revolutionary. Dogfighting, the circular turning battles that had defined combat since World War I, became secondary to energy management. Altitude equaled energy. Speed equaled energy. The pilot who could convert between altitude and speed most efficiently controlled the engagement. Captain James Habara became the first jet ace on May 20, 1951, shooting down his 5th and 6th MiG-15s in a single mission. His combat report described the new reality. They came down from 40,000 feet. We climbed to meet them. The engagement started at 35,000 and ended at 15,000. We were supersonic in the dives. The whole fight was vertical, up and down. If you tried to turn, you lost energy and died. The kill ratio favored American pilots dramatically, approximately 10 MiGs destroyed for every Sabre lost in air combat. But the ratio was misleading. Many MiG pilots were inexperienced North Koreans or Chinese. The Soviet pilots, flying in secret, were often more experienced than Americans and achieved near parity in engagements. More significantly, both sides discovered that jet combat consumed fuel at rates that made sustained combat impossible. A Sabre flying at full military power exhausted its fuel in 30 minutes. Combat maneuvering reduced that to 15 minutes. Pilots had to fight, win, or disengage and return to base before fuel starvation forced them down in enemy territory. The jet engine's appetite for fuel became the defining limitation of early jet warfare. Every tactical decision was governed by fuel state. Pilots learned to monitor fuel gauges as closely as their gun sights. Running out of fuel over enemy territory meant capture or death. Multiple pilots died attempting to glide jet fighters to friendly territory after fuel exhaustion, discovering too late that jets without thrust glided like falling anvils. Staff Sergeant Harold Fisher, an F-86 pilot shot down in April 1953, survived capture and later described the MiG-15 from a Soviet pilot's perspective, information gained during interrogation. They told me their engines were unreliable. Flameouts were common. The controls stiffened above 600 miles per hour, making high-speed combat difficult. But the biggest problem was fuel. They had maybe 20 minutes of combat time. If they couldn't force an engagement quickly, they had to return to base. Both sides were fighting with engines that remained fundamentally unreliable. The J-47 powering the F-86 required a complete overhaul every 15 hours of operation. The Soviet VK-1, their Neen copy, needed overhauls every 25 hours but suffered frequent failures between overhauls. Maintenance crews worked around the clock, replacing engines, rebuilding turbines, and repairing compressor damage. The maintenance challenge revealed another lesson. Jet engines were complex machines requiring specialized tools, trained technicians, and extensive supply chains. A World War II piston fighter could be maintained by a mechanic with basic tools. A jet fighter required precision instruments, clean facilities, and components manufactured to tolerances measured in 10,000ths of an inch. Korea demonstrated that the jet age meant more than fast aircraft. It meant transforming entire military logistics systems to support technology that was powerful but fragile. By the armistice in July 1953, jet combat doctrine had been established. Speed and altitude advantages determined victory. Energy management trumped maneuverability. Pilot training and experience mattered more than aircraft performance. And operational readiness, the ability to keep jets flying despite maintenance demands, was as important as combat capability. The lessons learned in MiG Alley would shape fighter design for decades, but while fighters grabbed headlines, the true revolution was happening in commercial aviation. On July 27, 1949, the de Havilland Comet, the world's first jet airliner, completed its maiden flight. Powered by 4 de Havilland Ghost turbojet engines, it could carry 36 passengers at 480 miles per hour at altitudes up to 40,000 feet, far above weather and turbulence. The Comet promised to make air travel faster, smoother, and more comfortable than any piston airliner could achieve. British Overseas Airways Corporation (BOAC) began commercial Comet service in May 1952, flying from London to Johannesburg with stops. The 6,724-mile journey took 23 hours, half the time of piston airliners. Passengers experienced a revelation: smooth, quiet flight above the clouds, none of the vibration and noise that made piston airliners exhausting. The Comet appeared to vindicate Britain's lead in jet technology. While America focused on military jets, Britain would dominate commercial jet aviation. Orders poured in from airlines worldwide. De Havilland couldn't build Comets fast enough. Then, they started falling from the sky. On January 10, 1954, BOAC Flight 781 disintegrated at 26,000 feet near Elba, Italy, killing all 35 aboard. Investigators found wreckage scattered across miles of Mediterranean seafloor. The cause was unclear. Metal fatigue was suspected, but not proven. On April 8, 1954, South African Airways Flight 201 exploded at 35,000 feet near Naples, Italy, killing all 21 aboard. The circumstances were eerily similar. Cruising at altitude, no distress call, sudden catastrophic breakup. Britain grounded all Comets. The entire fleet, representing Britain's commercial aviation future, sat idle while investigators searched for the cause. The Royal Aircraft Establishment at Farnborough undertook the most extensive aircraft investigation in history. They recovered Comet wreckage from the seafloor. They built a water tank large enough to hold an entire Comet fuselage. They subjected the fuselage to repeated pressurization cycles, simulating thousands of flights. After roughly 3,000 pressurization cycles, the fuselage failed. A crack had propagated from the corner of a window cutout, a point of stress concentration. Each pressurization cycle, each flight to high altitude, had extended the crack microscopically. After roughly 3,000 pressurization cycles, the crack reached critical length. The fuselage exploded. The disaster revealed a problem nobody had anticipated. Piston airliners flew at 10,000 to 15,000 feet, where cabin pressurization was minimal. The Comet flew at 40,000 feet, requiring significant pressurization to maintain breathable cabin pressure. Each flight cycle stressed the fuselage in ways that didn't occur in piston airliners. The fatigue failure mechanism was entirely new. De Havilland redesigned the Comet with thicker fuselage skins, rounded window cutouts, and reinforced stress points. The improved Comet 4 entered service in 1958, but the damage was done. Airlines that had ordered Comets canceled and turned to American manufacturers who had been watching Britain's mistakes and learned from them. Boeing, which had been developing its own jet airliner, the 707, incorporated every lesson from the Comet disasters: thicker fuselage skins, rounded windows, extensive fatigue testing before first flight. When the 707 entered service in October 1958, it was larger, faster, and demonstrably safer than the Comet. The 707 transformed commercial aviation. Pan American World Airways ordered 20, then 40, then 60. TWA, United, American, and every major airline followed. By 1960, jet airliners were replacing piston aircraft on major routes. By 1970, jets carried 90% of air passengers worldwide. The engines powering this transformation were descendants of Whittle's design, but evolved far beyond his original concept. The Pratt & Whitney JT3, powering early 707s, produced 13,500 pounds of thrust, more than 15 times Whittle's W1. More significantly, it was a turbojet derivative called a turbofan, where some air bypassed the combustion chamber entirely, driven by the turbine but not burned. This bypass air increased efficiency dramatically, reducing fuel consumption and noise. By 1970, high-bypass turbofan engines produced 50,000 pounds of thrust, with half the fuel consumption per pound of thrust compared to 1950s turbojets. The engine architecture pioneered by Whittle had been refined through decades of development into power plants that could reliably operate for thousands of hours between overhauls. The commercial jet revolution enabled globalization. Before jets, international travel was expensive and time-consuming, limited to the wealthy and the determined. After jets, it became routine. Business meetings across continents became feasible. Tourism exploded. Entire economies restructured around the reality that anywhere on Earth was reachable within 24 hours. The numbers tell the story. In 1950, worldwide airline passengers totaled 31 million. By 1970, 383 million. By 2000, 1.7 billion. By 2019, 4.5 billion people flew on commercial aircraft, almost all powered by turbofan engines descended from Whittle's spinning disk. But the revolution wasn't just commercial. Military jet development continued at breakneck pace, pushing into realms that would have seemed like fantasy in 1945. October 14, 1947, Edwards Air Force Base, California. Captain Chuck Yeager, flying the rocket-powered Bell X-1, exceeded the speed of sound in level flight, reaching Mach 1.06 at 43,000 feet. The sonic boom that echoed across the desert marked humanity's entry into supersonic flight. Jets couldn't quite match that achievement initially. The fastest jets of the late 1940s approached but couldn't exceed Mach 1 in level flight. But engineers understood that swept wings and more powerful engines would eventually break the barrier. The North American F-100 Super Sabre, introduced in 1954, became the first production fighter capable of supersonic speed in level flight. Powered by a Pratt & Whitney J57 producing 16,000 pounds of thrust with afterburner, it could reach Mach 1.3. It was also dangerous, earning the nickname Hun, and a reputation for killing pilots who pushed it too hard. The problem was aerodynamics. Aircraft behavior changed dramatically at transonic and supersonic speeds. Control surfaces that worked perfectly at subsonic speeds became ineffective or even reversed their effect near Mach 1. Pilots encountered inertia coupling, where roll inputs caused violent pitch oscillations. Multiple F-100s tumbled out of control and disintegrated, killing their pilots before anyone understood what was happening. Test pilot after test pilot died exploring the edge of the performance envelope. The names accumulated. Captain Milburn Apt, killed in the Bell X-2 after reaching Mach 3.2. Captain Evan Kincheloe, killed in an F-104 accident. Major Michael Adams, killed in the X-15 after a high-altitude loss of control. Each death added to the knowledge base. Each accident investigation revealed another quirk of high-speed flight. By 1960, fighters routinely exceeded Mach 2. The Lockheed F-104 Starfighter, optimized purely for speed, could reach Mach 2.2. With wings so thin and sharp, they required protective covers on the ground to prevent injury to ground crew. The McDonnell Douglas F-4 Phantom II, which would become the dominant fighter of the 1960s and 70s, could reach Mach 2.2 while carrying 18,000 pounds of weapons. These aircraft bore little resemblance to Whittle's vision of jet propulsion. They used afterburners, dumping raw fuel into the exhaust to produce additional thrust at the cost of massive fuel consumption. They employed variable geometry inlets that adjusted automatically to optimize airflow at different speeds. Their engines used multiple compressor stages, complex control systems, and exotic materials like titanium to withstand temperatures exceeding 2,000 degrees Fahrenheit. Yet the fundamental principle remained Whittle's: continuous compression, combustion, and expansion. The complexity had increased exponentially, but the basic concept of using turbine-driven compression to create thrust was unchanged from the garage in Rugby. The Vietnam War provided another testing ground for jet combat doctrine. American fighters, primarily F-4 Phantoms and F-105 Thunder Chiefs, faced North Vietnamese MiG-17s, MiG-19s, and MiG-21s in combat that revealed uncomfortable truths about jet warfare. The F-4, designed as a fleet defense interceptor, initially carried only missiles, no gun. Designers believed that supersonic missiles would make guns obsolete. Combat over Vietnam proved otherwise. Missiles frequently failed. Electronic countermeasures defeated guidance systems. Rules of engagement requiring visual identification forced close-range engagements where missiles were ineffective. Pilots found themselves flying Mach 2 fighters in turning dogfights at 400 miles per hour, exactly the kind of combat the aircraft weren't designed for. The MiG-17, a 1950s design far inferior on paper, proved dangerous in close combat because it could turn inside the heavier American fighters. The initial kill ratio was embarrassing, approximately 2.5 to 1, far worse than Korea's 10 to 1. Something was fundamentally wrong. The problem wasn't the aircraft, it was training. American pilots, trained for beyond visual range missile combat, lacked dogfighting skills. They didn't understand energy management. They committed fundamental tactical errors that got them killed. The Navy established the Fighter Weapons School, known as Top Gun, at Naval Air Station Miramar in 1969. The curriculum focused on dissimilar air combat training against aircraft simulating Soviet fighters, teaching pilots how to dogfight in jets. The results were immediate. Naval aviator kill ratios improved to 12.5 to 1 after pilots went through Top Gun training. The Air Force followed with its own aggressor squadrons and weapons schools. By the end of the Vietnam War, American pilots had relearned how to fight in jets, adapting World War II energy fighting tactics to supersonic aircraft. The lessons were institutionalized, ensuring future pilots wouldn't have to relearn them in combat.
Vietnam also revealed jet engines' Achilles heel, vulnerability to battle damage. Turbine blades spinning at immense speeds could be destroyed by a single bullet striking at the wrong angle. Compressor stages could be wrecked by ingesting debris. Unlike piston engines, which could lose cylinders and keep running, jet engines were all-or-nothing propositions. They ran perfectly or failed catastrophically. The A-10 Thunderbolt II, introduced in 1976 for close air support, was designed around this reality. Its twin General Electric TF-34 turbofan engines were mounted high on the fuselage, shielded from ground fire. The entire aircraft was built to absorb damage and keep flying, acknowledging that jet engines couldn't take the punishment that radial piston engines had once survived. By 1980, 43 years after Whittle's first engine ran, jet propulsion had become ubiquitous. Every military fast jet used turbofan or turbojet engines. Every commercial airliner except a few regional aircraft was jet-powered. Even helicopters increasingly used turboshaft engines, derivatives of jet engines optimized for shaft power rather than thrust. The industry Whittle and von Ohain had inadvertently created employed millions worldwide. Engine manufacturers like Pratt & Whitney, General Electric, and Rolls-Royce operated as strategic national assets, their advanced engines subject to export controls. A nation's jet engine technology determined its place in the military and economic hierarchy. The evolution continued. Fourth-generation fighters like the F-15 Eagle and F-16 Fighting Falcon, introduced in the 1970s, used engines with thrust-to-weight ratios exceeding 8 to 1, meaning the engine weighed less than 1/8 the thrust it produced. These fighters could accelerate vertically, climbing straight up like rockets. They routinely operated at altitudes above 50,000 feet, speeds above Mach 2, and G-forces that pushed human physiological limits. Fifth-generation fighters like the F-22 Raptor, introduced in 2005, incorporated stealth, supercruise, supersonic flight without afterburner, and thrust vectoring, engines that could redirect thrust for enhanced maneuverability. The Pratt & Whitney F-119 engines powering the F-22 produced 35,000 pounds of thrust each, enough to push the 64,000-pound aircraft past Mach 2 and to altitudes above 65,000 feet. These capabilities would have been incomprehensible to the RAF officers who dismissed Whittle's prototype in 1937. An F-22 produces more thrust than 73 of Whittle's original W-1 engines combined. It can fly 3 times faster than any aircraft in existence when Whittle filed his first patent. It operates at altitudes where the sky turns black and stars become visible in daytime. Yet it all traces back to that spinning disc in rugby. Every improvement, every innovation, every breakthrough built on Whittle's fundamental insight that continuous compression could produce thrust more efficiently than pistons at high altitude and speed. The commercial aviation statistics are even staggering. In 2019, before pandemic disruptions, commercial aviation generated $838 billion in revenue worldwide. Airlines operated over 25,000 jet aircraft. Manufacturers had order backlogs exceeding 14,000 aircraft, worth over $1 trillion. The global fleet of turbofan engines exceeded 60,000 units, each one a descendant of Whittle's design. The reliability had improved beyond recognition. Modern turbofan engines operate for 20,000 to 30,000 hours between overhauls. They achieved dispatch reliability above 99.98%, meaning fewer than 2 failures per 10,000 flights. The early jets that killed test pilots with regularity had evolved into the safest form of transportation ever devised. Frank Whittle lived to see most of this transformation. He witnessed jet fighters break the sound barrier. He watched jet airliners shrink the world. He saw his engine concept evolve from 480 pounds of thrust to 100,000 pounds. From irreliable prototype to extraordinarily reliable production engines powering global commerce. But recognition came slowly. The British establishment, embarrassed that they had nearly let the invention slip away, promoted him to Air Commodore and granted his knighthood. The financial compensation remained inadequate. American engine manufacturers made billions from technologies Whittle pioneered. He received speaking fees and consulting contracts, but never wealth proportional to his contribution. In his later years, Whittle expressed frustration at how close he had come to failure. In a 1982 interview for the RAF Museum, he reflected, "If any single thing had gone differently, the jet engine might have been delayed by years, perhaps decades. If my patent had been funded by the government in 1930, Britain would have dominated jet aviation. If it had been completely ignored, someone else eventually would have invented it. The margin between success and oblivion was frighteningly thin. I succeeded partly through persistence, partly through finding the right supporters at critical moments, and partly through sheer luck." Hans von Ohain, speaking at the same 1978 meeting in Dayton, offered a different perspective. "We succeeded because the technology's time had come. The materials existed, the mathematics were understood, the military need was apparent. If Whittle had not succeeded, I would have. If both of us had failed, someone else would have succeeded within a decade. Great inventions are inevitable. Individual inventors are fortunate to be in the right place when history needs them."
Both men were probably correct. The jet engine was inevitable, but the specific form it took, the pace of development, and the nations that dominated the technology were shaped by Whittle and von Ohain's individual efforts. Their parallel work ensured that by 1945, multiple nations understood jet technology, preventing any single country from monopolizing it. That diffusion of knowledge accelerated development. British, German, American, and Soviet engineers all contributed innovations. Competition drove improvement faster than monopoly would have. Within 2 decades, jet engines existed in dozens of configurations, each optimized for specific missions, from small turbojets for missiles to massive turbofans for cargo aircraft. The technology continues evolving. Modern research focuses on adaptive cycle engines that can vary bypass ratio in flight, optimizing for either fuel efficiency or maximum thrust. Hypersonic engines that can operate at Mach 5 and beyond. Electric propulsion for small aircraft, potentially revolutionizing regional aviation. Even concepts for nuclear-powered jet engines, investigated in the 1950s and abandoned, are being reconsidered for space applications. Yet all of it traces back to the fundamental insight that turbine-driven compression could replace pistons. That insight, developed independently by 2 men working in garages and small facilities, changed human civilization as profoundly as the wheel or the transistor. Consider what Frank Whittle's engine enabled. Global commerce is operating at speeds impossible before jets. Perishable goods are transported across continents overnight. Business is conducted face-to-face across oceans with minimal travel time. Tourism is transforming economies worldwide. Military capability projects power globally. Aircraft carriers launch jets that can strike targets hundreds of miles away. Air forces are deploying across oceans in hours. Strategic bombers can reach any point on Earth. Space exploration is built on technologies developed for jets. Rocket turbopumps use principles from jet turbines. Life support systems descend from high-altitude jet research. The entire infrastructure of space travel emerged from jet aviation. The global culture that emerged in the late 20th century, where information, people, and goods move at speeds that would have seemed magical in 1937, the shrinking of the world makes the person in Sydney or Seattle feel as accessible as someone across town. All of it, every bit, flows from a spinning disc in a rugby garage that produced 480 pounds of thrust for 15 minutes before its bearings seized. The final statistics, the numbers that capture the complete transformation. From Whittle's first patent in 1930 to operational fighters in 1944, 14 years. From first operational fighters to Mach 2 capable jets, 10 years. From the first jet airliner to jet transport dominating commercial aviation, 20 years. From 480 pounds of thrust to 100,000 pounds of thrust, 65 years. From experimental curiosity to powering 4.5 billion passenger journeys annually, 75 years. Total jet aircraft produced worldwide since 1945, over 500,000 aircraft. Total turbofan engines manufactured since 1960, over 180,000 units. Economic value of the global aviation industry in 2019, over $3 trillion annually. Frank Whittle died on August 8, 1996, in Columbia, Maryland, at age 89. Hans von Ohain died on March 13, 1998, in Melbourne, Florida, at age 86. Both lived long enough to see their impossible dream become a mundane reality. Both witnessed jet engines become so reliable and ubiquitous that most people never thought about them. That, perhaps, is the ultimate measure of revolutionary technology. It transforms from miracle to mundane, from impossible to inevitable, from curiosity to necessity. The jet engine is no longer remarkable. It's simply how aircraft fly, how the world moves, how modern civilization operates. But it began with 2 men who refused to accept that piston engines represented the ultimate limit of aircraft propulsion. 2 men who saw beyond the technology of their time to something that didn't exist yet. 2 men who were mocked, dismissed, and nearly defeated by skepticism and insufficient funding. They built the future in garages and small workshops with borrowed tools and makeshift equipment.
They survived failures that should have destroyed their dreams. They persisted through years when nobody believed, and they won. Every jet engine ever built, every supersonic fighter, every wide-body airliner, every turbofan pushing travelers across oceans, every engine powering global commerce and military might descends from their vision. The RAF officers were right to laugh in 1937. The spinning contraption producing 480 pounds of thrust was ridiculous compared to established piston engines, but they were catastrophically wrong about what it would become. Within a decade, that ridiculous contraption rendered every aircraft they flew obsolete. Within 2 decades, it had transformed aviation completely. Within 3 decades, it had changed human civilization. The mad engineer who built a jet engine in his garage didn't just change World War II, he changed everything. And it all began with a question nobody wanted to answer and a dream everybody said was impossible. The thunder of jet engines, the sound that now carries billions of people safely across skies worldwide, started as the screaming of a spinning disc in a rugby garage. They laughed at Frank Whittle in 1937. The world flies on his dream today.